You know, electricity is literally all around us, but the rules that make it all work, they are full of some pretty surprising secrets and honestly, some very clever simplifications. Today, we're going to pull back the curtain and uncover the foundational ideas that are so basic, they're practically hidden in plain sight.
So, let's kick things off with a real head-scratcher. Why do we pretend a simple copper wire has absolutely zero resistance, while that tiny little filament inside a light bulb has a ton of it? Well, the answer reveals the secret handshake of electrical engineering. It's all about the assumptions we agree to make. So, let's dive in.
Here's our game plan. We're going to start with the absolute basics. What even is a resistor? Then, we'll look at the two different sides of Ohm's law and expose its biggest hidden secret. After that, we'll tackle the super confusing world of short and open circuits. And finally, we'll see how it all clicks together in the great power balancing act.
All right, first things first, let's start with the most fundamental component of them all.
So, Section 1. What in the world is a resistor? Well, at its heart, it does exactly what the name says. It resists. Think of it like friction for electricity, or maybe like a bottleneck in a pipe that's trying to slow down the water flow. A resistor's one and only job is to get in the way of the current, and we call that property resistance. Simple as that.
Okay, so we know what resistance is. Now let's talk about the law that really defines it. I'm sure we've all heard of Ohm's law, V equals IR. But that famous little equation is actually a convenient shortcut. Its true origin is way, way deeper.
Now, this is where it gets really interesting. Ohm's law actually has two faces. The original version comes from something called field theory. It describes the deep, fundamental physics. You apply an electric field, E, to a material, and you get a certain amount of current density, J. That's the why of it all. But then circuit theory comes along and simplifies all that complex physics into the practical V equals IR formula that we can actually use. That's the how. It's how we build and analyze the circuits we use every single day.
So we have this incredibly useful law, V equals IR. It's the absolute bedrock of all circuit analysis. But let's ask the big question. Is it always true? Is this some universal law of physics that can never ever be broken?
In fact, let's just put it out there. When does this supposedly fundamental law completely fall apart?
And there's your answer. The single biggest weakness, the one thing that can bring Ohm's law to its knees, is temperature.
Okay, so here's the big secret. A material's resistance isn't actually a fixed number, not at all. It changes with temperature. For metals, when they get hotter, their resistance goes up. But for semiconductors, it's the total opposite. So the neat and tidy V equals IR relationship gets really messy in the real world. This is the crucial takeaway. The entire field of circuit theory is basically built on a gentleman's agreement. We all just agree to pretend that the temperature isn't changing, and that one little assumption is what makes all our math work out so nicely.
So, building on that idea of these perfect, ideal components, we've arrived at the centerpiece of this whole explainer. We're going to use what we've just learned to solve a classic electrical puzzle. What's the real difference between a short circuit and an open circuit?
Now get ready for this paradox. A resistor can be a short circuit and an open circuit at the exact same time. Now that sounds completely impossible, right? A short circuit means 0 volts. An open circuit means 0 current. How can one thing be both? Well, the answer is hiding right inside the V equals IR formula.
Okay, let's break this down, because this is where the magic happens. Look at a simple switch. When it's closed, it's a short circuit. The voltage is 0, but the current? It can be anything. It just depends on the rest of the circuit. Now when the switch is open, the current is 0, but the voltage across it could be huge. They're independent. But now, look at the resistor. Because its whole life is governed by V equals IR, the voltage and current are locked together. They are not independent. So, if the voltage across a resistor is 0, what does the current have to be? Well, according to the formula, it must be 0 too. And what if the current is 0? Then the voltage must also be 0. So an ideal resistor has the defining feature of a short circuit, 0 volts, and an open circuit, 0 amps, at the exact same time. It's this really unique state that only a resistor can be in.
All right, for our final section, let's talk about energy. We know how current moves through these things, but how does energy itself actually get around in a circuit? It all comes down to a really simple, really elegant balancing act. This is basically the universal rulebook for keeping track of energy in a circuit. We call it the passive sign convention. It's super simple. You just find the positive terminal on any component. If the current is flowing into that positive side, the component is absorbing power, using it up. But if the current is flowing out of that positive side, it's delivering power. It's acting like a source.
And this simple little rule leads to a really profound law. Some people call it Teligent's theorem, but it's really just the law of conservation of energy dressed up for a circuit. It just means that you can't create or destroy energy, you can only move it around. The power being delivered by some parts has to be perfectly balanced by the power being absorbed by others.
And that's the core idea right there. It's beautiful in its simplicity. For every single watt of power that's being delivered by something like a battery, there has to be exactly 1 watt of power being absorbed somewhere else, maybe in a resistor. The energy books always have to balance out to 0.
So we've just seen a perfect, unbreakable law of conservation play out in a tiny little circuit. And that leaves us with one final, much bigger question to chew on. If this elegant balance is true on such a small scale, what does that imply about the conservation of energy across the entire universe? Something to think about. Thanks for tuning in.